This screencast is about making data-based inferences about beta 1, the slope of the true regression line. Inferences about beta 0, the intercept of the true regression line, are made in a similar fashion. Inferences about the intercept, however, are used less often. This is a hypothesis test to determine whether the slope of the true regression line is different from 0. If the slope is 0, the model is not useful, since any x value would be multiplied by 0. The first step is to specify the null and alternative hypotheses. H0 says beta 1 equals 0. That is, the slope of the true regression line is 0. H0 says the model is not useful. The alternative hypothesis says beta 1 is different from 0. That the slope is different from 0 says the model is useful. The second step is to choose the significance level alpha. We impose a maximum probability of alpha on deciding that the model is useful, when in fact the model is not useful. In the third step, we write the model assumptions that affect the appropriateness of the probability distribution of the test statistic. These model assumptions are the INE model assumptions: independence, normality, and equal variance. There is a choice of two statistics, an F statistic and a T statistic. Both statistics result in identical p-values and thus identical decisions in simple linear regression. We present both statistics because they're used in multiple linear regression to test different things. The F statistic is MSR over MSE, the ratio of the mean explained variation to the mean unexplained variation. Large values of MSR over MSE indicate a relatively larger amount of explained variation and thus favors H1, that the model is useful. In simple linear regression, MSR over MSE is distributed with an F distribution with 1 degree of freedom for the numerator and n minus 2 degrees of freedom for the denominator. This is a graph of an F1 n minus 2 probability distribution. We'll assume that the computed value of MSR over MSE is here. Think about what we just said and shade in the p-value region on this graph. The T statistic is B1 over SB1. Large positive values of B1 over SB1 or large negative values of B1 over SB1 favor the conclusion that beta 1, the slope of the true regression line, is different from 0. That is, favor the conclusion that the model is useful. In simple linear regression, the T statistic has, if the model assumptions hold, a T distribution with n minus 2 degrees of freedom. This is the graph of a T probability distribution with n minus 2 degrees of freedom. Assume that the computed value of the T statistic comes out to be right here. Think about what we have said and shade in the two-tailed p-value region. In the fourth step, the computations are completed and the p-value is reported. When using Excel, the p-value for the F-test of model usefulness is reported in the right column of the ANOVA table. On the other hand, the p-value for the t-test is reported in the coefficients table in the p-value column. In simple linear regression, both of these p-values will always be identical values. In the fifth hypothesis testing step, we make the decision. We reject H0 and decide we have a useful model whenever the p-value is less than or equal to the significance level. On the next 2 pages, there's a specific example of this hypothesis test that uses the F-test statistic. Then on the 2 pages after the next 2, the same hypothesis test is completed, except this time using the t-test statistic. Both of the examples are based on 30 observations of assessed values and market values of single-family homes in the same area of a city. The question is, can the independent variable assessed value be used to predict the dependent variable market value? You should work through these 2 examples. An FYI, there's a hypothesis test to determine whether beta 0, the intercept of the true simple linear regression line, is different from 0. This test would use the t-statistic B0 over SB0, and if the model assumptions I and E held, would have a t-distribution with n-2 degrees of freedom. The p-value for this test is reported in the intercept row of the coefficients table. This would be the p-value. You will not be required to perform the hypothesis test for the intercept in the homework. It is used far less often. It would be appropriate to pause this screencast and work through these 2 examples before proceeding to the material on confidence intervals for the true slope and true intercept. On the second from the last page in this section, material is presented on 100 1-alpha% confidence intervals for the slope beta 1 of the true regression line and for the intercept beta 0 of the true regression line. Recall that if alpha is 0.05, then 100 1-alpha% would simply state 95%. This screencast will discuss only the 100 1-alpha% confidence interval for the slope beta 1 of the true regression line. The 100 1-alpha% confidence interval for the intercept beta 0 proceeds in a similar manner and should be read. An understanding of both of these confidence intervals will be needed to complete homework 3. On the last page of this section is exercise 3. Exercise 3 asks for a 95% and 90% confidence interval for the slope of a true regression line. You should complete the solution. As a quick review of how to interpret a 95% confidence interval, we can say, if this expression for a 95% confidence interval for beta 1 is used in 100 independent situations, about 95 of the confidence intervals obtained would actually capture the value of beta 1, and about 5 of the confidence intervals would not. In this expression, B1, the slope of the estimated simple linear regression line, is at the center of the interval. The quantity T alpha over 2 n minus 2 times SB1 is subtracted from B1 to obtain the left-hand endpoint of the interval, and then is added to B1 to obtain the right-hand endpoint. The numerical value of B1 is found on an Excel coefficients table under Coefficients. The numerical value of SB1 is found immediately to the right of B1 in the standard error column of the coefficients table. For example, on this convenient coefficients table, B1 appears here and SB1 appears here. The value of T alpha over 2 n minus 2 is obtained from a t-table or through the use of the Excel t-inverse function. For example, if the data involve 30 observations and we wish to compute a 90% confidence interval, then the value of T alpha over 2 n minus 2 would be T 0.05 with 28 degrees of freedom. A t-table appears in these notes in 2 pages. If we look for the value of T 0.05 with 28 degrees of freedom, I think we've done this problem before. Here's the 28 degree of freedom row, so we'd be looking across that row, and we'd be looking down the column that had 0.05 at the top. So as we move down this column, we get to the number 1.7011. That would be the T 0.05 with 28 degrees of freedom number we would need to compute the confidence interval. A final and important observation is a 95% confidence interval for the slope beta 1 always appears on an Excel coefficients table. Before moving to the homework, it would be a good idea to complete exercise 3 on the next page.